So thank you very much. So let me first thank Professor Patnaik for inviting me and giving me an opportunity to speak on superconductivity in a metastable simple. So there is nothing unconventional actually. I should have because there is no conventional superconductor. I think people don't want any more conventional superconductor. But something we found interesting, so that's why we started working on it, because it's a simple cubic. Simple cubic is the whatever known simplest structure among all the sets. So it's interesting to see simple cubic structure and then superconductivity in simple cubic structure. So that was our idea. So we all know the simple cubic structure with one atom basis. So that's very important. So mostly you will see in a elemental metal or an alloy disordered, chemically disordered. So that's a possibilities. So, but this structure is not stable compared to FCC and other structures, okay, HCP and so on. So we know that. So there is a lower coordination number, so it's 6, and the only element what we know which is stable at ambient condition is the alpha polonium, but it is radioactive, and it was predicted to be theoretically a superconductor, but I don't know whether anybody has looked at it, but I do not know about existence of superconductivity in this, and there is no other material which is stable at ambient conditions. So obvious reasons for low packing efficiency and low density, obviously, so weaker metallic cohesion, and this has a metallic system and it has a tendency to distort and go into the due to soft boron modes, distortion to low symmetry. That's a spontaneous distortion can occur in this. So of course when you go to alloys and you have an electronegativity difference, then we end up having the in ordered systems. So, and these are the problems with the simple cubic structures, and 3 shorter SBSB distance and 3 longer SBSB distance in this system. So this is what you see at ambient condition. Okay, the structure is rhombohedral, and which is a semi-metal. So, and there was an experiment very old, and they apply pressure at room temperature, okay, and about 8.5 GPa. They did not look at the structure, so they thought it could be a simple cubic, and they found superconductivity in this system when you cool it low temperature, obviously. So these are the superconducting transition at various pressures. At what you see here, even they said at low temperature they remove the pressure, it is possible to retain, but with finite Tc, about 2 Kelvin or so. So it was possible, and it was studied in 1969. Okay, so the other thing, as I mentioned, other possibility you have simple cubic is alloys. So you alloy them and then disorder, make chemical disorder, and still possible to make simple cubic. There are few papers on this, and one is on this superconductivity in the same title with that various kind of alloys, including gold and antimony, and they studied and possibility. They said there could be there is a superconductivity, but still what is the phase which is responsible for superconductivity, high pressure, was not clearly demonstrated until these people. They worked on these 3 elemental system, and they found forming simple cubic, but there is a lack of what is this superconducting properties and other details, chemical stability of the simple cubic phase. So it's not that whenever you make the material and retain it, like in diamond for example, so it is stable for ever millions of years at room temperature, okay. But because it's very stable materials, you have a covalent bond, and these metastable materials are very small, deep in the free energy, okay, small. So it depends on the energy of activation or the energy barrier. So a material can be stable, metastable, or what we say kinetically stable, okay. So the stability aspects were not known, and detailed superconducting properties were also not looked at it. So, and that's what aim of this our study. So we prepared this material, and we selected one composition which can give you highest TC in this composition alloy. So we did by 2-step process. One is the arc melting with suitable composition of AU and SB, and then add extra AU and make it the composition close to SB 8.3, 0.83 and the AU 0.17. And this is the cell configuration. So it's a cubic anvil type. So you can apply pressure and then apply temperature, and you can quench it after heating. You can remove the temperature quickly within 2 minutes, and then release the pressure slowly. Okay, so you will be able to stabilize this cubic phase. So that's what we see. And when you look at this is the X-ray, so you can see this corresponds to the simple cubic but chemically disordered, as you expect from this composition. And if you look at more carefully this the peak shapes, and there is an asymmetry on all the peaks, okay, on the higher angle side, so indicating a quite inhomogeneity or strain in this sample, which is very obvious. Okay, you apply this metastable phase from a rhombohedral to cubic phase, which is obviously is not a very stable phase. So, and you have a lot of strain, and then even chemical inhomogeneity in this. So, and then the lattice parameter is close to 2.98, and yeah, when we look at the susceptibility, zero field cooled, and very nice transition with the 8 Kelvin TC, and the volume fraction is close to 94%. So it's a bulk superconductivity. The transition is quite sharp, and also demonstrating type 2 superconductor. Okay, so now I come to the stability aspect. So which I mentioned, diamond is quite stable. So we take a material, we apply pressure or temperature, you transform this phase to an A prime, another structure. Okay, then you remove the pressure or temperature, you end up having the same material to start with, like antimony. For example, they did the experiment, apply pressure, got superconductivity, remove the pressure, and come back to the original, which is semi-metal. Okay, this is one type, so it's reversible phase transition, like the textbook example, sodium chloride to cesium chloride, as we can understand from the displacive transition. So it will come back to this. So the another material or another type is, so you start with your material and apply pressure and temperature, and you stabilize another phase. Okay, there is a phase transformation, and when you reverse P and temperature, of course, when I say that we have to quench it, because to stabilize this metastable phase, so you retain this metastable phase, like diamond or any other phase transformation, you can stabilize it, unlike this phase. So this is what we know, that I have also made several other compounds of different properties, and most of them are stable for at least several years. So we have seen, and we can understand this. But the surprising thing in this compound is that that we wanted to do some measurement after some time. So the student wanted to check the property, and he looked at this volume susceptibility, which is equal to 0.7%. So that's what first we found that, and then he looked at the X-ray, and what we found is it is completely decomposed within 70 days, roughly. Then he did systematically, that was first observation. He did systematically and various, number of days, different days, and then he looked at the X-ray, and then he found that slowly it is decomposing. So at least for a week, it's stable, and we could make all the measurements within that time. So, and then we tried, I told him to look at very carefully, and then he did in another batch of sample. So complete decomposition, it takes close to 3 months. So it's completely transformed to the AU SB2 and then SB. So at room temperature, it's a very short span of time. So this kind of things are not, many compounds are not known to exhibit like this. So most of them have a large enough barriers or activation energy, so it requires significant time to transform. But this within short span of time, so it decomposes and into these almost the starting composition, and try to analyze it with this Avrami fitting and the nucleation growing of these phases, and we see different phases, like looking at this value of the N here, and I didn't go into the details, but what is important is you have the what it gives you is the 3D growth of antimony and then 2D growth of the AU SB2. So this is what one can understand from this decomposition. So I try to understand this. It gives you very good implications for other materials. So this kind of phenomena. So I already discussed about the type 1 and type 2, and this one is again similar to type 2, but it's not strictly, we should not call type 3, but there is a time dependent, very short time, okay, because of the energy of activation. So it's kinetically unstable, like the kinetically stable phase like diamond. So, and that's what we see in this system. So it's very interesting to see such thing with time dependent phenomena. So as I said, one aspect is the looking at this chemical stability. So that's what we found, that chemical stability is, it's not stable like a diamond, but it's a very short duration, and at room temperature it can decompose into the starting materials. So it crystallizes. So it's not an amorphous. So you have AuSb2 and antimony, what you see in the X-ray. Yeah. Then we look at the all the superconducting properties. So it's nothing. It's more like conventional, except I will just tell you the difference. So normal measurements at M versus H. So to find out the JC value, and then to find out HC1. So at various temperatures, and we use the same estimate, and at HC1 at 0 field is 12 millitesla, and the TC is 8.1, close to what you observe. So, and then we look at the normal state resistivity, and so this is, we try to analyze with the Bloch-Gaussian model, but it doesn't fit very well. So we need to take the saturation aspect of the scattering, and that fits reasonably well. So, and that's what's shown in this parallel resistor model. And we also estimated the HC2 from the temperature dependent, field dependent of the resistivity from the 50% criterion, and we estimated HC2 which is about 1.1 Tesla. So you can suppress superconductivity, with small field, and you look at the normal state properties. So then we move on to the heat capacity. So this is the heat capacity at 0 field and then 5 Tesla. So when you apply 5 Tesla field, so you can see you can fit with the gamma T plus beta T cube and phonon contributions, and it fits quite well. And we can estimate the electronic contributions by subtracting the phonon contribution. And what we found is, so our BCS model, simple BCS model, could not be fitted very well, but we needed an alpha model to vary the n. And what we get, delta is 2.02 or roughly 2, and which indicating a strong coupling superconductivity in this system. Okay, so yeah, so. And another aspect what we see in this is the heat capacity. So this is the phonon part, by fitting the Debye and Einstein model fits very well, and there are two about 15% of Einstein contribution and 85% coming from the Debye contribution here, and we try to fit the parameters obtained here, theta d, theta e are given here, and you can see the theta is lower than the theta d. Okay, so, and most importantly, that we plotted the C by T cube versus T, and you can see at 5 Tesla, which is in the normal state, and you see a boson peak, okay, indicating or further supporting that you have a strong coupling superconductivity coming from lattice spin electron phonon coupling. So yeah, these are various parameters obtained from the different measurements, including measure the Hall measurements. So the carrier concentration is coming between AU and SB, so about 10 to the power 22 and so on. So, and so what we see in the Uemura plot, and our material does not fall onto the simple metallic system, Okay, so it's close to the alloy, so indicating again possible strong coupling superconductivity in this system. So the electron phonon coupling obtained is close to 0.9, and with the help of Professor Vaidiswaran, so we have did DFT calculation. I'm sorry for this slide, so I think it's too much of stress, and we took because of the disorder, he took 3 into 3 supercell, and he obtained the electron density of states. So we can see the total density of states, and mainly this is coming from the antimony 5p, and there are small contributions only from antimony 5s and AU. Okay, and he also found the band structure, which is there are I think 7 different mode crossing the Fermi level with 3 hole type and the remaining electron type, so causing the multi-band metallic electronic structure, and which are shown here in the Fermi surface. Okay, so all this our studies indicate a possible large enhanced electronic density of states. That means the AU substitution modifies the antimony electronic structure and then increase the density of states, and also increasing electron phonon coupling, and which is also responsible for the decomposition, which is not really a stable phase. So it is a kinetically unstable phase. So there is a competition with superconductivity instability of these phases. Okay, so you have indication of soft phonon and strong electron phonon coupling in this, and this is the summary. And we have also tried recently to obtain MEOSR on this. So this is the transverse field MEOSR, and what you see in here is the TC, the T temperature 9.1 Kelvin, which is above the TC, so in the normal state. So what you see, you don't see any damping here, and this is what you expect. Okay, and but when you cool to below TC, so you have a damping at low time, so indicating possible first I must say that there is no time reversal symmetry breaking, but there could be possible field penetration, and these are the values, but still this is not complete, but we try to use the single sigma and then try to see the external field was about 200 oersters, and what we see in the superconducting is the same field in the paramagnetic state, but when you go to the superconducting state, as you can see that it reduces to 137. Okay, so that's what we expect, and the sigma has increased very significantly. So this is what the equation we try to use this. So the background contributions, and then the external field, and then superconducting B field. So to understand, get an idea about the symmetry of the order parameters, so we plotted the sigma independently at different fields, and then you can see as you increase the field from 200 to 500, so it decreases. So that's what one would expect, and what is shown here is sigma versus external field, and it goes with what we expect from this field dependency. And again here what is shown is field at different applied fields versus the temperature of the system. So you can see that the higher field is 450 about or close to 500, and which decreases but which increases close to the TC. So all these behaviors are what is expected consistent, but when we try to fit this average data for the sigma at different fields, but it doesn't fit very well with the single gap model, okay, BCS single gap model. So we are still working on it to improve this, and also that we observe a dip here. So we don't understand here, but what we expect is a constant, but what we see a small dip, and I think I asked for the error bars there, so it is within the error bar or not. So this currently we are just looking at it, so I think soon we will have an idea about it. So I think I must summarize. So we have the kinetically unstable simple cubic phase, which is stable only for 2 months or 3 months, and depending on the batches you make it maybe. So the origin of superconductivity, you have the enhanced density of states and metallicity coming from the AU modified electronic structure basically. So if you look at the average electrons, actually it should reduce it, but it modifies the electronic structure. And then you have the soft mode phonon coming from the boson peak evidence. There seems to be a strong electron phonon coupling, and which we are trying to do theory further on this. And much more than what observation is, it has a broader significance, and this provides a route to recover high pressure phases as a kinetically unstable materials. Okay, that's one thing that for example, I mentioned RP phase nickelates. So these nickelate phases are not stable at ambient condition. So you need to apply pressure and temperature to see or just pressure alone to see the superconductivity. You cannot retain that phase at ambient pressure. So we need to see at what conditions you can retain these phases at ambient conditions. Then it will be interesting to look at the various properties. So right now we are limited by the high pressure, so you are not able to study all the properties of these materials. So it's looking at superconductivity in simple cubic system is rare, and making this AUSB alloy significant. I think there are possible other alloys can also form with this disorder simple cubic phase, but I think this is enough to demonstrate. So I want to acknowledge the PhD students Savik Banerjee and the postdocs who are also involved, and the collaboration with Vaitishwaran's group, and also the MESR data coming from ICES for Bitterbecker and Ria. And finally, I just want to tell those who are using neutron and MESR in ICES. So I think you are aware that we have a project between DST and RAL. Last 6 years we have run, and it's completed first phase. The next phase is starting, I think this month it should start now. So we have received some money also, but there should be a formal signing of the agreement. So we are waiting for that. Otherwise we can start this now. So the phase 2 program starts between 2026 and 2030. And please inform your colleagues also, and we will send out notices. I'm just waiting for this agreement to be signed formally to send out, so I don't want to do it before. And I think we need to, DST wants new users to be, since I have time I take this. So I have completed my talk. So this is for general people, so that's why I kept some time. And they want to introduce new users in this. So we will also organize workshop to introduce neutron and muons to new users. And we need to train also. This is one demand by the DST. So otherwise only only some 10-15 groups are only using it. So they want many users. So I think we need to help the expert users, need to help others. And so I will send later about circulate this notice. So thank you. Yeah.
Thank you, Professor Anderson, for your talk and finishing in time. So the session is now open to questions. Certainly, please.
So, since you mentioned that this is electron phonon coupling sort of driven superconductivity, did you also sort of try something like a isotope effect type of a thing?
No.
So we have evidence that it is electron phonon?
We're just proposing from the whatever experiments we have done. Okay. So we have not done clear, because it's a simple cubic centrosymmetric. You cannot do any Raman things. So it looks,
I see.
Yeah.
And also it's very interesting that gold is very robust, or very, what do they say? I mean, it's very, it doesn't want to be superconducting, but you sort of,
it take what?
When combined with SB, so it's very strange how gold and SB.
Yeah, the contribution density of state, it's very small, AU.
Okay.
It's mainly antimony. Antimony.
Okay.
I think it's chemically, I think majority it's chemically it's helping to form that structure. Yeah, there are many other alloys which can form also. So that's why I'm saying that it's possible that it's mainly coming from antimony, stabilizing in a simple cubic structure, and it's possible to stabilize at ambient condition. That means kinetically in an unstable state even, at least for a few months. So yeah.
And one small, I just wanted to know what is the HC20 of this?
HC20 is 1.1. Yeah,
1.1
someone. Yeah,
Tesla.
yeah, 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 yeah.
So thank you very much. I have actually. I would like to know what is the superconducting volume fraction?
It's 95%.
95%.
Yeah, yeah.
Okay.
After correcting demagnetization factor. Yeah.
Okay. Okay.
Yeah.
So then, actually, if I am allowed, then I have some more queries. Okay. So you showed actually in your heat capacity, which is the thermodynamic probe.
Correct.
Which is essentially one of the important
Correct,
probe
correct.
for the superconductor.
Bulk superconductor. Yeah.
So there, basically, we saw that it's actually you try to model it
Correct.
by electron-phonon coupling.
Yeah.
And when you go to the Meosat data,
Yeah.
when you see the sigma, which is
Yeah.
actually indirect measure of your superconducting order parameter.
Yeah.
So there also it doesn't really fit there.
Yeah.
So have you tried to do it with kind of multi-gap systems?
We are right now trying. That's what I said. Without completing. So I just wanted to present the present status of it. So we are trying that multi-gap. It didn't work at least. Yeah, it didn't work. Yeah. The other models we are trying.
Any other question?
I was curious, why this composition particularly?
This was showing the highest TC. That's it.
I see.
Highest
So
TC.
other-
Yeah, the other things will come down. Other composition.
So you have tried other compositions? They showed
It's
over-
already reported. The other composition. Yeah.
Okay, any more questions? So if there are no more questions, so let us thank the speaker once again.